Okay, is this working? Apparently is. I This is my second attempt. I first tried, but I was having too many uh, adjustments to be made live. So I created here a skeleton just to get started. So I'm going to do my first implementation of this suffix array induced sort algorithm. I found it very insightful. I don't know how well or whether I will be able to do this implementation successfully, but I'm going to walk through what I've learned and some of the ideas and why this algorithm is interesting. So first, what it is, like the definition. Basically, the idea is we take any string and we take all the suffixes, so slices of the string starting at an index I to the end, and then we can sort this. So this is one example for strong string, and so we can see, like here, we have a string followed by strong string. So if we do this, we have on log n comparisons, and each comparison is on. So the complexity is on squared log n. So why is this algorithm useful? Well, one of the application is to find repetitions in a long sequence. It can be any 1D data series like genomic data, or could be a corpus, some long text. We could use this, for instance, for plagiarism detection. If a certain number of words is repeated, we can assume, oh, this was copied from somewhere. And or we could use this for audio analysis or any other applications of 1D data. So how complex would be an algorithm to identify repetitions on a string? So this is one where we select all the possible starts and end. Okay, that's too complicated. We can do something simpler, taking this I2 loop for out and making an J2 here. Actually, instead of J2, we will have to put plus I1 minus J1. This is the length of the string. So we could say this as an n, and this is a range going from 1 to len s minus j1. This is going to stop in len s minus j1 plus j1 len s. So if we say I1 plus n, j1 plus n, j I1 plus n, and j1 plus n plus 1 here, because this is, so this would be something, it's not completed, we'll have more adjustments, but this would be O n cubed. So still a long a difficult to compute algorithm. But what it does, well, here we can see that it identified the positions where we have repetitions, and if we go here on this sorted string, those are going to appear together. So that's a very interesting application of this. So how could we do this in a very simple way? We could take the indices after sorting tuples of the suffix and the index, then and how can we check? Well, for every index I, the string starting in AI is smaller or equal to the string starting AI plus 1. So here an example in this strong string, but in order to compute this, we can treat every character as a number. So this is so we are going to use NumPy arrays to do that. So this is the skeleton of what we are going to do. Actually, this is what my first attempt to create this live. I started to write this and then I stopped. And so T prefix types. Every prefix is defined as a L prefix or S prefix according to this notation here. And so this is the lecture notes that I am using as a reference. And then we also have we have to identify the LMS, the leftmost S-type suffixes. So the definition is that an S suffix is smaller than an S plus 1 suffix. So again, this could be done as something like L if S I less than else S, or next is S L for I in range len S. String index out of range. Let's do this here. So this is how it works. Let's see if it matches the convention. There is a convention for the last being always S. So if we make these, and we can also put this in a tuple with the character just to have an idea of what is. There we go. Actually, this one here we append a special symbol that is less than every other symbol, and no, we don't need this plus one, or do we? then there we go. So L, yes, so it matches the I'm not sure here if I should count as an S for the equality or as an L, but anyways, it's not going to have any equality because the prefix starting in I is never going to be equal to the prefix starting in I plus 1. But yeah, again, this is comparing the entire string, so this is not efficient. We have to implement, what we have to implement is something that goes backward on the string, making a recurrence. So how it will be like? Get, actually not prefix, suffix type from a string. We have to create a bucket for each position. So we'll have let's define the types as well. So L type will be ord L, S type equals ord S, just to make it easy to read as well. Then for T equals is a good suggestion, and we want T minus 1, or let's say N equals like S. Tn is S type. Is it S type? Yes. And then again, completion is nearly good. So this is there as well. So if character I is less than Si plus 1, then for sure this is going to be an S type. If it's greater than, then for sure it's going to be L type, and otherwise, actually else, and this is good as well. So what is going to happen if we have a repetition, or okay, where is here? Do we have a repetition in these examples? Don't know. Like here, GG. In this case, it means that at some point the characters are going to go down. And if we are closer to that point, then the suffix is smaller. So the suffix si is going to be of the same type as the suffix si plus 1. So that's one thing. The next is get bucket boundaries. To get the bucket boundaries, we have to count each of these. So I'm going to specialize these to u into 8. I'm not going to make it generic yet. So get bucket boundaries. So for sure we are going, so let's have a count that's also good, is guessing correctly. Is this, no, this is not a good guess. What we have to do is for I in range n c s I plus equals 1. Yeah, now it's correct. And then later we do a cumulative sum that's going to give us the boundaries. So the first boundary is always going to be 0, and the other boundaries are going to be determined by how many characters smaller than that are available. So let's put this in a separate cell and test it. So let's make this into a variable. As bytes equals this, then text, boom, not text, code. And we create a test for get suffix types as bytes. Is out of bounds because, okay, s plus 1. Let's use n because we defined n somewhere. Zeros of n plus 1 still says okay here if it started at n minus 1 and it's trying to access s. Okay, it's trying to access s out of bounds, so let's create this as a special type as well. T n minus 1 is always going to be of L type, and this is going to start from n minus 2. So now we have, and we can do to string, and then so 2 bytes as it's suggesting. Then we can have something like this. Does it match? S, L, L, S, L, L, S, S. Looks like the same. All L and then S. So, and now what about the bucket boundaries? This is going to be a long this is wrong. I shouldn't have accepted blindly. So this is going to be 260, could put even 257, and then we could give this plus 1, but you have to be careful because let's say in B array with the type int 8 plus 200. How much is this? 44 is going to wrap around. So we probably just keep as is, and instead of trying to give an extra slot to the 0, that would make it too complicated. Yeah, get bucket boundaries. We'll give. We have to return, of course. So we have. It's not correct yet because okay, and this is not u int 8. This should at least be u int 16, but let's make it 32. So still not there because this is not n plus 1. This is 256. Okay, now we have the correct. So this is probably the dash. We have then possibly a G appearing twice. Then we what would be here G appearing twice, I appearing once, N appearing twice. So this is telling where the bucket for each letter is going to start. Yeah, that looks good. And now the LMS indices. So the LMS, oops, so I shouldn't remove that. Should I? No, I can't remove that. So def get LMS indices on T. Well, I only need T. Does it make sense? Does this make sense? Yeah, kind of. Actually, we can just instead of getting this, we can already populate as to use T, the bucket boundaries. Let's call it B, and let's take let's also take an array where we are going to write. So how will this go? We have to scan from right to left. And we start from N, we go down to minus 1. Oh yeah. Then if T I equals S type and T I plus 1 equals S type. So this is one situation where is so we have A. Apparently it knows the algorithm because it's predicting very well. B S I plus 1 will be I plus 1, and then this B is going to be S I plus 1 is going to be decreased by 1. Is this going to populate all of them? I don't know. There is maybe some corner cases at the very end. I know that there is this special symbol here. This makes the algorithm so code. So what? So let's go by these steps here. T equals S gets fix S bytes. C equals get boundaries. A, that's good. Populate LMS positions. And then we print A. Let's see what populate LMS positions. It's not defined. String index out of range. String? No, just index. String index. Wow, because I'm sending an S somewhere. S, where is it? Okay, no. I'm using this S. Ooh, yes, we need the S. So S, that will be actually S bytes. Forward given. Okay, so let's make this will be let's consider with the prefix the sentinel where S bytes equals S string encode, but with this. I don't know if this case is going to work because the dollar might not be the lowest character. So now I simply use this here. It should be n minus 1 here. That is the last index. So now we get something, and we could, let's say, zip this with sorted S just to to string, just to see. It's better to simply say s plus dollar. That is what we wanted. So now okay, that's 0, 6. We have this I as an LMS position. Kind of working. We have more corner cases here. But anyways, let's go to the induced sorting. That is so the induced sort has 2 passes, one going left and one going right. So what we'll do here is this correct? Actually no, this the left pass uses the S types, and we have another similar in this sorting right TBAS. If T is L type, then we put this and is missing B. There is another issue here that okay, so this is the right. For the left we need this -1, and we have to increase here B S I -1 plus 1, and here we have to decrease B S I and the other thing is this is modifying the B array, so we probably have to send a copy or to make a copy or to have something. So I will create this C and then a B equals C copy, and then every time I send how should we handle this, because we want to it's going to make it a little bit uglier. For now we can send a copy. We can always send a copy of C.copy, and then but this is going to allocate memory. So we probably want something simpler, just a copy of the content without allocating new memory. So once we populated the LMS positions, now we can do an induced sorting right. And no, actually first, yes, and then induced sorting left. What do we get? We have to run this cell first. In here for the LMS we don't have all because of then because you're stopping at no, we are running up to -1. But we so we go up to 0. 0 is the last, and then so what are we getting now? Let's see. Let's see. The only thing that is not working as expected here is this position. I would expect this to have an index because it is an LMS by definition, so we should have that index. But why we don't have? Because you're starting from no, it's not an. Oh yes, it is. Okay, but that's a special case that I will have to add manually. It will be B Z S n -1 A on that position will be equals n -1. N -1, no, it's actually n. Here n as well. Okay, now we have everything in place. So the next is summarize string. There is a very interesting property of this algorithm that after we finish these steps, we get all the LMS blocks in a sorted position. So what is an LMS block? An LMS block is basically the string that goes between two LMS. For instance, here we have an LMS and here we have an LMS. So the characters in this sequence, in this block here, is an LMS block. So let's find that. Where's here? So this is an example where it's taking the LMS. So C, G, G, C, A. Then, so the way to so okay, summarize. Summarize is going to take all of these blocks and give a name, a unique name for them. So let's do that. This this name could be either a multi-character thing, or it could be an integer. Problem here is that we are using uint8. Maybe we have to change that to use a larger number, like a larger number of characters, but let's start with this. So code tag. So we have, what do we need? We need the type, and we need the string, and we need the indices. So how does it work? We scan the array backwards. We could even say for I in a minus 1. Then we say if the I minus 1 equals L type, and if the I is S type, so this means I is an LMS position, then we have to take this segment as one block. But how can we? So we know that these are going to be sorted. Well, actually I could do this left to right, is not a problem. Left to right or right to left. That's an interesting one, because I know for sure that the first here is going to be an LMS position. So I could go well, maybe I just take the I as is. So I in range 1 len, or let's call n equals len a should minus 1, no? Is the last index guaranteed to never be an LMS position? I guess so. And we can call prev equals a0, and let's say current equals ai. And now what we have to do, we have to this is not getting very Pythonic, and this is a bit frustrating, but basically I'm going to have an n, not n because you already used, for let's say j in range current minus previous. then what do you say? If, yeah, that's it. This is going to be a false. But not only that, what I need is I'm going to create an array with the indices and another array with the block names, let's say. Actually, I'm going to do this in 2 passes. I'm just thinking now that if we do in 2 passes, it's going to be easier. So we can do LMS positions equals. Let's make an array. I was sort of optimizing, but let's forget for now. And then we just say LMS positions append A0. Oh, sir. And now LMS positions append AI in here. I'm going to go through the LMS positions. And then I'm going to go so first, actually, I could start appending here an artificial one. And no, or not, maybe not. Let's make a complicated loop here. While L equals 0, while say I1 equals LMS positions I2 equals LMS positions I plus 1. I1 plus L less than N. And actually I only have to check I2 plus L and I1 plus L doesn't exceed I2. And if S I1 plus L not equals S I1 plus L, break, else here we have name equals 0. Let's call it 1. Let's start with 1. In here we just have name plus equals 1. we can LMS names, append name, and we have to, LMS position is ready, so it's good. And this goes up to the second last, not the last. And in the end, we have this, and we have to return both the names and the positions. This was a bit more Pythonic, but I'm sure this is not going to be the most efficient, just not as efficient as the other implementation, the other functions. I would have to optimize them. Would have to optimize this one later. But one thing, so now let's see what goes with summarize string. What do we need? T as bytes and A. Is that all? Possibly. Please typo append here T. And here boom boom. I've got an infinite loop here. So we have 1, 2, 3. So we have no repetitions. What does it mean? It means that this A should already be the correct one. So what does it come with? So A, how does it look like? And now let's check the reference. 13, 16, sorry, 13, 6, 12. Looks like the same. Let's see. Let's put them together. So print A, print the reference. Are they similar? 5, 10. Here they're different. So I didn't get to because now that I have this, I have to do 2 other induced sorts, no? So what is it? Get buckets. So this is part of the implementation. You can put here. Remove these springs. And now we got, say, S. Okay, then what do we have to do here? Now, okay, so what happens is that this is giving the LMS blocks in the correct order. 13, 4, 7. 13, 4, 7. Before, when we scanned the string to populate these LMS positions, we just went by the order that they appeared in the string. So what we did was 13, 7, 4. Now we are going to repeat this with basically this one. So we are going to take create a very similar let's say fix LMS positions with, we don't need the T anymore because you already know that they are, but we need the B. We need the B? Yes, we need A as well. And we need, let's call an LMS here. And then we have to go by the LMS in reverse order. Let's n equals then LMS. We go for I in range and -1, -1, -1, and here we can simply say A, B. Oh, do I need the S? Yes, I need S. A, B, S, I equals I and B, S, I equals return. No, we don't need to return anything. So this is going to update A in place. So here, what we do is, I'm going to ignore one. Yeah, it's I'm going to ignore one step here, but that is as a IS on this. I'm going to keep it like, because I know that for my example it's or I can do. So if I do this, then it's going to return LMS A. Is LMS A here? What do I need to do is I need to get the sorted suffixes. That would be basically LMS sorted. Here I'm starting to make it inefficient. LMS name. Actually, I want just the indexes. I for I LMS A. And then fix LMS positions. Who is B? So it's C. Copy. A continues being A. LMS sorted. And then once I did this, I can just repeat the two in the sort steps, and hopefully return A is going to give me something. This was probably okay. A, B. Isn't this just what we did here? What is it? Okay, 1, 2, 3. 3, 13, 4, 7. But I don't think this is going to change anything, because is the 4 the same as the 7? No, they are different strings. So if this is not sorted, is not this last step that is going to fix it. So let's see again. A ref suffix array of S. Okay. This was supposed to be very easy. Okay, here's maybe an issue. No, is it an issue? Si-1. No, it is correct. Is it maybe a problem that I'm using -1 here? Let's try. Now it's No, because then we get out of of index, of out of range. Index error. And what if we show this as I or I in A? Looks good, good. I orange. Oh, so this is a problem. O came before N, S came before R, strong T before S. Oh, okay, so no, because this is actually because I have these extra positions. Strong string. I already spent 1 hour, so I'm going to give up on this. I'm going to fix it later.